So my name is Tomer, and I'm the CTO of Modela AI. Modela is a CRD-based end-to-end AutoML system on Kubernetes. And I want to present, so what I'm going to present, basically the first part is about AutoML. If you know AutoML, it might be generic, it might be basic or beginner for you, or might not. I wasn't sure what is the audience. So basically we're going to cover what is AutoML, the AutoML benefits, and what AutoML cannot do, the actual search space. So the manual search space, what do you need AutoML? Like in order to understand why you need AutoML, you want to understand what involved in creating a good pipeline in machine learning. And then I'm going to cover search method. I don't know, it is part of cutting, but I'm not sure people understand like how the algorithm works inside. And then a little bit of NAST, which is neural architecture search. And I'm going to present the AutoML benchmark, which is used to compare AutoML systems. And then we're going to dive into Modela. Basically, I'm going to explain why you need Modela and what is Modela. And then Modela does auto stuff, which is behind the training, which is auto DataOps and auto MLOps. And I'm going to show a demo. Now, I did design the lecture for half an hour, so it might be a quick one. Okay, so what is AutoML? So basically, the idea behind AutoML is that it's kind of a black box. You get the input is the data, and the output is basically one or more ranked pipeline. Now, the AutoML system itself is kind of a search, right? We want to find the best pipeline for us based on our data. So the data is key here because it's going to drive the AutoML search. Another two things that are going to drive the search are our constraint, which can be in time, how many models we want, how much hardware we have, what kind of hardware we have, or we want to search on GPU, etc., and our objective. The objective, again, is based on the data. So based on our task, what do we want to optimize? And at the end, we get pipelines. So a pipeline is a full ML pipeline, or if you do a NAST, you get a deep learning model. And in addition of a pipeline, what we want to get is we want to have the pipeline as a Docker container so we can deploy it. Preferably, the AutoML system can also deploy it because there are cases, for example, an AutoML system that run as an IoT. We don't really have control of it. And then in addition, we want explanation like Shapley values, feature importance, a model card, which usually it's a report, and the metrics, the training metrics, testing metrics, etc. Now, AutoML system, of course, need hardware. This is the big cost in the system. So we want to manage infrastructure efficiently. For example, we want to run on spot instances. And if you run it as part of a team of data scientists, then you need collaboration. Like you want to review the output of the system. You want to approve models, so you cannot just put model in production. It's called ML governance. So this is like the AutoML system. Okay, so the AutoML benefits. So basically, it's for the benefits. The idea with any data science, the benefits of a data science to the business is you want to get more value of your data. Now, if you use an AutoML system, you can get more models in production, which means that you use more data, more value as a result. In addition, the business can use non-ML experts. You give them this tool, and they have power to create models. Now, for the non-ML expert, and this is my goal personally with Modela, is you want to create and optimize models on your own data. So, for example, if you're a doctor or if you're a researcher and you want to you have a biological data set that you created with not a lot of rows, but a lot of columns, what you want to do is you want to be able to create models with no code, so only using GUIs and clicks. You want to understand those models, so you want to trust them. And of course, you want to understand the prediction of the models because you're going to take decisions based on their prediction. So this is my goal. This is why Modela is a pure no-code system. Now, for the ML expert, which is, I assume, a Kubeflow goal, Kubeflow and Katib, Basically, they want to make you more productive. Modela also, but the idea here with the ML expert is that they give you a way to efficiently, systematically train your model. So you don't rely on intuition. You drive your models based on the data. And the system, like the AutoML system, should do automatic feature engineering, feature selection, should give you better accuracy against the average data scientist. Of course, if you go to Kaggle, you see what AutoML system do. They never win the first place. But if you look at the average performance, they're usually in a very good place. And then it can give you a baseline for manual machine learning. It generates automatic interpretation like Shapley values, feature importance, AUC curves, all what you need in order to understand the model that it's created. As a byproduct, it's also you get automatic experiment management because it manages the leaderboard, etc. And it supports multi-objective optimization. Okay, so what the AutoML system cannot do. So the first thing, of course, AutoML system cannot understand your business. So it doesn't know about your business objective. So this will always be the data scientist or the data analyst will always have a win in there. Also, it cannot collect your data. So you must come up with, in generally, a labeled data from different systems. There are AutoML system lately that can, you give it a schema of a database and it can generate the important features, but they are not widely used. It doesn't have any domain knowledge, which means that it cannot constrain by itself the domain of the search. So if you know that the hyperparameter in your search is very specific to the search, you can join the system and you can save a lot of time. But it cannot know it by itself. Most of the system doesn't deploy the models, and there's the fairness. It doesn't know the fairness parameters, like what kind of protected attribute it has. And most of the system don't do lifecycle management. So most of the AutoML system today, what they do, the actual open source system, what they do, they basically just train the best model, the best pipeline, but they don't do deployment, they don't do drift detection. There's no CI/CD, concern for latency and hardware. Okay, so now what I'm going to do, I'm going to define what the AutoML system does manually, and in order to understand why it's so hard, like why it takes a long time if you want to do it manually, and what it does automate before we go into AutoML systems. Okay, so and also like in the blue is basically the Kubeflow itself, because it's a Kubeflow meetup, and I assume that you know what is Kubeflow. I want to refer to Kubeflow as our reference point if you know what is the Kubeflow component that does that. Okay, so the first thing the AutoML system do is the data, and the problem with the data is that there's a lot of problem with data. Okay, so first we have, we can have a wide data. So imagine a 10,000 feature, 1,000 features data, depending on your field. You can have a small data, so like only 1,000 rows because it's very hard to label. And then you need to consider different post-validation methods. You have a different data types, like tabular data, image data. So you need expertise in the data type, like time series. And then the data, of course, always come with errors, usually the real-world data. So how do you do imputation? Do you need to normalize the data? How much errors you have? There's different decisions that you need to take, like what kind of imputer you use based on your missing values. And of course, the problem that you need to do it for every group of features, like your categorical features as handling, the numerical features. So you need to imagine like for every feature in your data set, you might want to have a different processing, etc. So the data is handled in the Kubeflow pipeline data preparation. Okay, so now we have data cleaning. Okay, so here what I'm gonna cover I don't know, now I have time, but okay, so basically what here, there's the Kubeflow pipeline feature engineering. So this is the feature engineering stage. In this stage, what we do manually is we want to do data cleaning and feature engineering. So for categorical features, usually we do, there's special imputation for categorical. How do we encode them? Like do we use one-hot encoding, label encoding, or target encoding? How do we handle many unique values? And how do we handle rare values? For the numerical features, Basically here we want, again, we have imputation, mean, median. Do we want to scale them? How do we handle outliers, robustness to outliers? How do we have skew? How to detect skew? How to handle skew? How to handle target skew? And then outliers. How do we going to handle outliers? For the unstructured features, so this is like text or images. The problem here is basically encoding. So we have a text. Again, how do we want to encode the text? What is the tokenization? Do we want to use stemming? Do we want to use deep learning model like Distilbert, BERT, etc.? And then this area which above our data, which how do we generate features? So here we have like univariate generation. So for example, especially in time series data, how do we generate logs? How do we generate windows? And then we have multivariate, for example, for integer features, we can use different binary operator on the features. So this is the feature engineering and feature cleaning. Okay, so for the feature selection, basically, why do we want to do feature selection? Because most of the features are not predictive. And if you use only the predictive feature, we can make simpler model, which doesn't overfit. And especially each feature adds noise to your data. And this is very dangerous because the model can train on the noise. And if you have a lot of features, you can get, overfitting. So feature selection. So here there's a special method. There's like 3 areas. There's filter methods, which use statistical way, like variance and correlation. There's wrapper methods, which basically define different set of features, and they either move forward or backward. So it can start from an empty set and add features, and then they train model and see if the feature added to an objective. This is very expensive to do. And the most common is embedded method, which basically you train like a random forest, and then you look at the feature importance and decide which feature to keep. And of course, you can, again, this is also the different method, and you want the AutoML system to find you the best features. So this is, again, Kubeflow pipeline feature engineering. And the ML algorithm itself, this is, if you go to Kubeflow pipeline training, what you have is the ML algorithm. So basically here, again, this is called the cache problem, which means that you not only want to select the algorithm, each algorithm that you select has its own hyperparameters, right? So it's like a dependency in the hyperparameter space between the algorithm and the parameters. So here, what we want to do is we want to AutoML system, of course, sample the algorithm. Again, it can sample from linear algorithm, gradient boosted tree, IGBM, etc. And if you do a neural architecture search, it doesn't sample algorithm, but it samples the structure. And then in addition to that, so this is, again, it's a huge space by itself, but you also want to create ensemble. Especially if you want to create the most accurate model, usually those models are ensembles with different degrees and different based algorithm and different method. So stacking ensemble, average ensemble, etc. So as you see, without an AutoML system, and this is my belief, it's going to take you a lot of time if you just rely on intuition, and there's no reason really not to use an AutoML system, especially if you can run it on a cheap hardware, or if you can run it locally. So this is the thing. Okay, so now we go, okay, so what is AutoML system? So AutoML system, we take our manual system, and we basically need to automate everything inside. So it includes the cleaning, feature engineering, algorithm, and hyperparameter optimization, which is called HPL. Okay, so now we're gonna go into the search. So the main thing in AutoML, like the most expensive thing and most of the time of the system, the computational time, is in the search. So there's different kind of search method I'm going to cover later. What the Kubeflow component for that is called Khatib. Khatib does hyperparameter optimization. But the idea with the search is that you can have either parallel search, a distributed search. You have concern over like fault tolerance. What happens if the search will be distributed? What happens if some of them not die? You're concerned of experiment management, so you want to follow the search and see where it is, because those searches can take it can take 4 hours, and if you do deep learning, the searches can take days, even weeks. So you want to make sure that the search, for example, can do checkpoints if you train neural nets. So you want the search to continue. It should be fault tolerance. And then, of course, you have the notion of storage, like if you do a parallel search, how do you access the common storage? And like, how do you optimize the cost of the search? Like, how do you use the spot instances? How do you share GPU, etc. But the goal of the search is generate those pipelines and run them. So at the end of the search, you want the best pipeline. Okay. So I'm going to cover the search method. You might know that we call it, I don't know, it's not that cutting edge, but I'm going to cover them and you might enjoy. Okay, so the grid layer. Okay, so first of all, we're going to cover the grid method. So the idea with the grid is that you create, very straightforward, you create a grid of configuration. The problem with the grid is that, first of all, it doesn't naturally support continuous hyperparameters. So you need to divide them, to discretize them in order to create those grid points. Now, the main problem with the grid is that explosive in the combination of the grid points, right? So if you have, it's two, basically like n. So it's basically explosive to the number of hyperparameters. And then another problem is that with the grid search is that you might use your compute time in exploring areas which are not important. Like, for example, here in the picture, if you do grid search, we will only search those 3 points which are important, but we also spend time on this non-important hyperparameter. So the grid search, you can use grid search, but only for very small number of hyperparameters. Okay, so another very common thing is to do random search, which is actually very common because it has very good properties, especially if you have a parallel search system. So the idea with random search is that we just walk on the search space from node to from point to point, and we just sample point on the search space, and we can sample as many as we want. And if we have a parallel search, then we can basically parallelize all the search there. Now, the good thing about the random search is that we might during the search we probably going to cover a lot more points which are important. So we might converge into a good configuration. However, we have no memory. So if we have an expensive evaluation of a single model, we're going to pay a lot of computation time, which is not good. However, this is a good method if you have a lot of hyperparameters, because the other methods are kind of constrained to that case. So if you have a lot of hyperparameters, random search is good. Okay, now we come into the state of the art. It was the state of the art, which is Bayesian optimization, which is one of the methods that is used in most of the optimizer. So what is Bayesian optimization? Basically, in Bayesian optimization, what we have a surrogate model. And the classical Bayesian optimization from the first paper, that appeared in 2012, is the Gaussian processes. So the idea with Gaussian processes is basically a regression, Gaussian process regression. Basically, it's a regression that doesn't output a single value, but it outputs a Gaussian values. So, for example, if you look here, our prediction from the Gaussian processes is this like black is like the distribution, the uncertainty is here, and this is the real function. So how does the search work? Basically, we evaluate a point, and then basically we train the Gaussian processes to predict those Gaussian distribution on each of our search space, and then there's something called acquisition function, and the acquisition function will basically tell us where to search next. And the acquisition function is moving between exploitation and exploration. So at the beginning of the search, we're gonna explore the space, and once we find like the points like here, we start to exploit the space. So the search is basically two functions working together, And the best thing is that because we have this acquisition function, we basically try up to 50x less models. I just want to note that during the explore phase, Bayesian behave like random because it basically explore the space. But once we have like around 25 or 20 models, we start to getting this exploitation and we get the benefit. Now, the problem with Gaussian processes is they cannot handle categorical variable. So the field move into random forest and TPE, if you heard this notion, which basically instead of training a Gaussian process a regression model, we train a random forest model. Okay, so this was for the classical algorithms. Now for the NAS. So the idea for the NAS is basically that our search space is composed of layers. So we don't do algorithm search, we do an architecture search. So we have layers, and we have and for each layer, the architecture is like node per layer, a number per layer, as well as the activation function. So the idea is that we basically search architecture, or there's something called a cell, which means that we have like one or more layers together, and we search those. And the search strategy, again, is the same. We have a random search based on optimization, as I explained before, reinforcement learning, and something that is called hyperband or ASHA. With hyperband or ASHA, it's called a model-free search. The idea is that you don't run the search because it's expensive to evaluate a model up to all the iteration. You just start with a lot of models with not a lot of iterations, small amount of iterations. You train them, and then you select the best third. You train them, give them more budget, and then the best third. It's called successive buffing. Now, in order to accelerate the search, the problem with NAS is that it takes a long time. In order to accelerate the search, there's something called low modality, which means that, for example, if we train on the images, we first train on low resolution images, get the best model, and then continue the search on the right resolution. So this is the search. Now for the post search, usually what you want to get is all the experiments that you did, the HP importance, Shapley values. Some systems generate the actual code. You get the model card, which is the report, and the ready content. Okay, so this is the AutoML system. So just I'm going to go on every one of them. Okay, so we have the open source AutoML toolkit. A notable mention is the AutoGloon from Amazon, which has a different architecture. If you want to read about it, it's a very interesting product. And the Microsoft Flamel. And then, of course, Katib and Kale from Kubeflow, which is open source AutoML. And then we have the commercial AutoML platforms. Of course, and the leaders in the field are H2O Driverless and DataRobot. Those are the first companies that actually commercialize in a cloud, it's not a cloud specific. And then the cloud offering, most of the cloud. For internal platform, honorable mention is FB Looper. I suggest that you read the paper. It's basically an AutoML, it's a new AutoML system in Facebook that is fully declarative. And then we have the Bayesian optimization, open source libraries, etc. Okay, now the AutoML benchmark. The idea with the benchmark, so why is the benchmark? The idea is that the AutoML community, everyone was training on a data set that like good for his or her framework. So they decided to create this general benchmark based on something called OpenML, which is a collection of data sets. The benchmark contains 71 classification data sets, 37 regression data sets, and each data set like have a different characteristic, like imbalanced data, a lot of rows, a lot of columns, etc. And then basically, if you have an AutoML tool, you run it over the benchmark. Okay. So this is the AutoML benchmark. Okay. So now I'm going to go into Modela. I don't know if you have questions. So I'm going to go over into Modela. Okay, so what is Modela? So the idea with Modela, it's a kind of, I think it's one of the first platform which is totally pure Kubernetes. The idea with Modela is that I see Kubernetes as a platform and not as a container orchestration tool. Because Kubernetes has very unique design with the CRD and the declarative and the intent-based behavior. So I designed Modela as the ML platform. Like Modela is the ML platform on top of Kubernetes. Kubeflow is also. So this is Modela. Now the benefit of Modela is that it's a pure Kubernetes native, so there's no code. There's no Python code or any other code in all the ML, the ML lifecycle. So it's fully CRD. It's fully CRD based. It's fully declarative, of course, because it's used only CRDs. And it's end-to-end. It has DataOps, the training, the AutoML, post-training, and MLOps, which is the production. It contains within itself quality control, so you can attach declarative unit test, statistical unit test, to the data and to the model, and Modela will run them. In the first release, it supports many tabular data and time series, which is mainly like business focused. So it supports regression, classification, forecasting, and group forecasting. And it is self-hosted. So all the models and all the data set that you create, like Kubeflow, you run it on your own hardware, and basically you don't upload anything to anywhere. It's like up to you. Modela will manage the actual storage for you. Like it can connect to any data lake, and it's managed the actual configuration. So you don't need to do anything. And of course, Modela itself is self-managed by the Modela operator, which is follow the operator patterns in Kubernetes. Okay, so how does Modela does the search? So the first thing that we do, of course, everything is declarative. So the first thing that we do with the data is we define a data source CRD or data source CR, submit it to the system. Modela will infer the data types and will automatically create those unit tests and everything. So a data source defines the schema of your data. And then for each data that you have, you can submit a data set. A data set contains, and then what Modela will do is going to analyze the data set, profile it, visualize it, make reports, find outliers. Everything is automatic. And then it's going to alert you also. So it has an alert CRD or alert CR that you can connect to any notification via the notifier CR. So it's fully automatic. It can connect to a lot of data sources, all the common databases, common cloud databases, etc. And then here we can see how this is part of the dataset CR. So you see, so for every column, Modela compute all the statistics possible, and those statistics are going to drive the design of our feature engineering and feature selection. Okay, so this is the Modela AutoML search. The idea here is that the Modela will use the data. So you can define something called a study, which in Kubeflow, in Declarative, it's called experiment. And then you define, and then the study, so Modela will take this study and use an optimizer, or I call it a designer, to start designing, efficient pipelines. And you can select what kind of optimizer you want. Modela is using Optuna under the hood. And then you can see, so in order to make a no-code, the Modela API has the full definitions of scikit-learn. Like all the algorithms are there and all the hyperparameters are encoded in the Modela CR and Modela CRD, as well as XGBoost, CADBoost, LightGBM, as well as PyTorch. So you don't, instead of writing Python code, basically the Modela model CRD contains this. So this is, for example, an estimator in Modela. Yeah? And of course, the same is true for all the scikit-learn feature engineering. So this is, for example, the feature engineering pipeline in Modela. And of course, you can define feature engineering pipeline per column or per feature. So you have different type of those. Like you see, like these columns, you have different pipelines. We're going to see it in the video. Okay, and this is this. And of course, Modela also does the automatic feature selection for you. It's part of the model. Basically, a model CR contains the full pipeline, including the algorithm, etc. So as I said, Modela is not just an AutoML system, it's also an auto DataOps system. So the DataOps part are this. So you have a connection CR, you can connect to MySQL or S3. You have a data source, we define the schema, the format, and the data unit test. You have a data set, which defines visualization, profiling, unit test result and outliers, and you have the report. So basically, what happened with, like when you define a data set and you process it, it's going to generate a report. And of course, the AutoMLOps. So each model we can define. The AutoMLOps is driven by the Predictor CR. The Predictor CR is drift detection, auto scaling, etc. And the prediction is logged. Again, Modela is self-managed by the Modela operator. You can see it here. So to install Modela, you just install the operator, and it's going to install Modela itself. And this is the Modela architecture. Basically, on the master node, Modela runs the control plane and the data plane. Modela is stateless, so all the state is stored in the data lake. And when Modela train a model, there is a job, like the trainer, the trainer container, basically compile from the model into Python pipeline, run the code, and report the metrics back. Modela, like each object in Modela is a TTL, time to live, in order not to strain etcd. So the CRs are garbage collected into long-term Postgres. And of course, the predictor, and then there's also the predictor, like if you want to have real-time prediction, the predictor CR is like running in the cluster. In order to access Modela, you have the SDK, the UI, or you can use kubectl. Now, instead of Kserve, Modela, there is the predictor let, and it is based on the Google Gene framework. And the idea is that every request passes those stages. We have authentication stage, we log the prediction, we do validation, monitoring to Prometheus, drift detection, which is the feature histogram CR. So for every feature, Modela has a live distribution, and then we can compare those to the training data in order to find it. And of course, at the end, requests are either go to the model or the shadow model. Okay, so now it's the demo. The demo is, I didn't know how much time we had, so the demo is, I'm going to show the demo screen. So the demo is basically, can I share my screen? Can you see my screen?
I can see your screen, but we don't see the demo playing.
Let me start to share the demo screen. What do you see now?
We see the demo. We see the tab in Chrome, I think. Yes. I see your mouse moving.
Okay, let me just stop this. I'm going to start. I'd like to share the screen itself.
So now we see the.
Do you see the demo now, Ron?
Yep, we see it moving.
Okay, but this is the demo. Okay, yeah. So let me start from the beginning. Okay, so it is recorded because it can take a lot of time. So the idea is that so now we define the data source. So the demo is going to show how you do a churn prediction. Okay, so basically you define the data source, you infer the schema. So this is a customer churn data set. So you create a data source, then you create a data set, and everything behind the scene is Kubernetes native CR. Data location. Okay. Now we create a data set, so Modela will ingest the data, profile it, and it manages everything in the storage for you, like in the data lake. You can see that everything is a Kubernetes job, so you can get the details of the job, the logs as it's running. Here in the data set. All right, so now it's done. You can go into that and you get a full profile, automatic profile of your dataset statistics, the feature types, the statistics for each feature, you get histogram for each feature. And then Modela generate a lot of visualization that it's going to later put in a report that you can send. Okay, so now we have the data set. We're going to do a study. A study has two phases of optimization: the feature engineering, finding the best feature engineering, and then finding the best pipeline. And of course, you can control, this is the constraint, you can control how many trainers. And there's a lot of advanced options. If anybody wants like a personal demo, just contact me. We can go over it in the real demo. Yeah, so what the study will do is gonna first start, so I'm gonna go here. It's basically gonna start a lot of feature engineering pipelines, trying the best feature engineering. And then this is, for example, a pipeline that Modela generated. We can see that Modela dividing your feature into high cardinality categorical, low cardinality categorical, numeric pipeline, and numeric pipeline with outliers. And everything that you see here is the model CR. It's like a no code thing. So we take it from the model CR. It's going to train all the feature engineering with the same algorithm because we want to get the best feature engineering pipeline. And then now it started to do the real training using the best feature engineering. Yeah, this takes like a long time. It also depends on the algorithm that you select. But everything is like version optimized. So Modela is sure that you get the best result like in the minimum amount of time. And everything is running on your own machine, so or on your own cluster. Yeah, so now Modela finished the search. It's going to do the test on the test data set. It selected random forest. Yeah, now it's going to run the unit test, going to generate Shapley values, do the model profiling, and this is the complete model. If you look at the model, what Modela is going to generate confusion matrix. There's a lot of metrics and a lot of stuff that Modela generate based on the training. So it has confusion matrix. It's going to generate matrix on the cross-validated dataset, RC core, precision recall core, feature importance. This is the best model. Going to generate all the confusion matrix, PR curves, yeah, Shapley values, Shapley summary. Yeah, and now if you want to deploy a model, now it's the AutoML you can release the model to production. Now the model is live, and you have, yeah, you're going to see here, basically what we have now, we have an automatic MLOps. So we're going to watch your features, and we're going to alert you on feature drift automatically. And you can make prediction from this screen. So yeah, so you get the screen that you can just try to make predictions. So you can set value for the feature, you do predict, and you see the result. In addition, what we have a DataOps CRD, which is a generated dashboard in Streamlit that you can give the URL to non-ML expert, and then they can log into the Streamlit. We use the ingress. Yeah, so it basically, yeah, and you can do a single prediction. You can predict, and you get the result, and Shapley. Okay, so this is it. So now I'm going to share. Okay, what do you see now?
Your desktop.
Okay. Okay. Apologize about that. Okay, you see the slides?
Yeah, we see your slides.
Okay, so just a quick overview for the CRD. Again, the data product CRD. For each data product, we have a namespace, and then we have data CRDs, training CRDs, and inference CRDs. I think that I covered everyone. Modela has support for the data pipeline and a recipe CRD, which is basically an Excel. So it implements around 230 functions that does the data processing using recipes. And also covered here, yeah. And the batch prediction is the prediction. And also Modela, the CI/CD Modela is the model pipeline, and it supports like different environments if you go. And then the Modela is a multi-tenant base, so you have the tenant CR, and inside the tenant you define the infrastructure CR. So, for example, connection to other systems, accounts, a bucket for storage, and notifier. There are two special namespaces: Modela System, where all the Modela parameters reside, and the Modela catalog, which is describe Modela itself. Like all the algorithms that Modela use, are defined declaratively in the Modela catalog. The actual training is done in the Modela lab. So the lab CR define the lab, serving site CR define a serving site, and then the data product. And so if you look at the lifecycle, basically this is just a mapping. I just added this slide because, but basically you can see that the Modela CR cover all the lifecycle. So the business understanding, we have the use case, which is the data product. You can attach artifacts, etc. The data understanding, which is the data set and the data source. Data preparation, which is the data pipeline CR and the recipe CR. The modeling, study and model, which is the AutoML. The deployment with the predictor and DataOps, and a feature list.